Thanks for joining us today. Modal testing, the practical considerations. I'm going to talk about a lot of modal items you may need to consider when you're doing a modal test. You know, from planning the test to transducers and shakers and hammers, a lot of questions. These can be presented in a lot of ways. We're just going to try to keep it small and bite-sized things today with links for further exploration sent out at the webinar review later this week.
Yeah, so we'll just, Bruce said there, we'll cover a few things, just things to think about as you're setting up the test, how to choose certain sensors or hammers or shakers, whatever tools that you may be using, and then some other items to think of for troubleshooting purposes, even when you're running into little challenges during the test that always seem to inevitably pop up. So, we'll start off with what is modal analysis. So we aren't going to go into a deep dive on what it is, but at its core, it's just the study of how a structure responds while being excited. So we're looking for natural frequencies, mode shapes, and damping. Then we're typically going to take this information, we're going to use it to either validate a finite element model, so that way you're able to make some choices in your conceptual design phase versus waiting till the end product to find out there may be an issue. And when we're doing this, of course, we're going to have to excite the structure in some means, maybe through a hammer, a shaker, or just as it is in the real world, more of an operating deflection shape kind of measurement. So we'll go through a few different methods of all that. But ultimately, why do we care about this modal analysis? Why is this something we're going to do? So again, ideally, we're making all these choices earlier on in your conceptual phase to improve durability, so you don't have, say, excessive wear on a tool or a tool breaking due to some odd vibration at a certain operating speed. Major consideration when it comes to automotive, any noise or vibration that gets to the occupant, that is a quality issue. May not necessarily be a issue where something's going to break, but it is a quality challenge. Then you get into your safety realm. So obviously this is where we can't have stuff fail when under operation, or even if there is an excessive vibration on a machine that a person's operating, and at that speed it shakes a lot and can increase that vibration dose to the operator to the point where you have a human vibration problem now because of a resonant frequency of that machine. So cuts across kind of all breadths as to why this sort of testing is important. A few good examples that many of us might have seen over the years. So this isn't a photo or a video of the Tacoma Narrow, but it is a example of a mode shape of just a typical bridge. But if you can recall or have seen the video of Tacoma Narrows, if you haven't, just YouTube it. It is basically catastrophic failure of a bridge from that drove it to a residence.
And I wanted to note too, this video and the next video we'll look at were provided by Vibrant Technology, the ME Scope. It's a great, you can even do photorealistic visualizations of modes. So right now, see some various modes, obviously exaggerated. Tacoma Narrows was kind of a funny example because it was so exaggerated. You could almost see, it was a, maybe not a classical modal example, but it's often viewed as classical modal failure. But you could see that mode, the mode shape essentially so strongly. But often you're not going to see things like this. But another visual provided by the team at ME Scope, you can kind of see mode shapes going on. This is, GBT testing to assess AEROELASTIC phenomena like FLUTTER on a GBT test on a plane. So I think it's kind of important. Today we're going to talk about the practical considerations when you're doing a modal test. We're not going to go into real depth of anything, but Chad kind of laid out the summation of what we're trying to do today. One thing I want to talk about is what modal testing isn't. And if you did a big Venn diagram of intersect of usefulness of general vibration testing versus modal, they do intersect sometimes. And I find it pretty interesting how sometimes people that don't need to do structural testing or even vibration testing at all often confuse them. And I guess we as a manufacturer don't make it a ton easier because a lot of our shakers can be used to test both. But a general vibration test is usually if you're going to qualify something, you're going to excite it with force, acceleration, or a specific displacement, or you're replicating something environment, or you're just going to run it till it fails. And test equipment like that, you could do it so the shaker supports the item under test. You could do it like a closed loop, force limited type of thing, or environmental testing, where you thermally cycle or do, control some other parameter while it's going through this. Do this one.
Sure. Yeah. So, modal testing and converse are being that most typically you're going to see that the structure is going to be self-supported or supported in some other means like a free with bungees or something of that sort versus being supported directly on the shaker. And another big difference to draw is we're not necessarily trying to drive the item under test any specific sort of vibration level that you might be with like a force limited vibration test. We're simply just trying to excite the structure enough, whatever that may be. It can vary structure to structure, but just enough to excite the resonant frequencies and the modes so that we can then observe its response and learn about that structure. So
often, another good example is often a modal testing may be an open loop system. You just want to measure the force that you're putting in. You don't necessarily, you want to make sure you're providing adequate force to the entire structure, which we'll talk about, but it's quite a bit different than the closed loop general vibration testing that we'd seen in some of the, in the previous slide. And, a modal test, just some other differences. It may be quick, you may excite your structure for a lot shorter of a time. And I don't know that either one is particularly exciting to watch, a modal test or a general vibration test, but modal test can be a little boring to watch. You think something really exciting is going to happen from seeing all the exaggerated that you can draw engineering conclusions from. But in reality, it's you're just going to hear a lot of noise or a lot of sine sweeps or chirps.
Yeah, and so when you're beginning your modal test, it's always, this is something that maybe you can throw back to the days in school when you first learned the basic assumptions of what modal testing is. But these are always a great set of criteria of your basic assumptions to keep in mind. They can be actually very useful from a troubleshooting point. If you have we do assume that structure is linear typically to start with, but not all structures are linear, and that can certainly drive what you're using, shaker versus hammer, to excite the structure. Time invariant, so that can be kind of sneaky in a sense. Let's say you've got a part that is temperature sensitive, so in the afternoon the sun's shining on it, whereas in the morning the sun's not, and you're getting different measurements if you're testing in the morning or in the afternoon, even in the same day. Little details like that can sneak up on you and really kind of make you pull your hair out for a second while you're wondering why your measurement varies, when, as far as you can tell, nothing else has changed in your setup.
So one good tip there to interrupt quick is a lot of people, if you're going to start, roving sensors or something, before you change, try to eliminate things like time invariance. And if you're doing the next setup the next day, keep your structure set up the same way that for the prior day. Fire everything up the next day and do another quick sanity check on your test. Duplicate what you'd done before. Make sure everything's the same before you start varying and moving sensors or doing anything where you can vary the structure.
Yeah. And if you're roving sensors, you might also be using a dummy mass to maintain that mass at your sensor location. So you might have only a few sensors, but more dummy masses that are moving around to maintain that time invariance. Then Maxwell's reciprocity is another good quick check that you can use to check linearity. So your input at one point and your response to the other should be the same if you reverse the input and response point. So easy to check with something like a modal hammer. Of course, can also the shaker, just a little more effort to move the shaker around. But yeah, a good way to see if the structure is indeed linear. Then observability, it's just simple. Are you able to both completely excite the structure and have enough response points to actually measure what the structure is doing, or at least measure the modes that you're curious in? You may not be curious in very high frequency resonances or high level modes, but if you're curious in a few of the lower ones, it is certainly good to make sure you have adequate coverage.
Okay. And I think it's important to note too that always it's tough to really put this into a slide, so I just want to say something now is as good a time as any. Always keep what your test goal is in mind at the forefront of everything you're doing. Make sure that nothing you're doing kind of strays you from what you're testing. It sounds ridiculous, and it's hard to really think of an esoteric example that I can share, but make sure you're not chasing something that isn't what you really need to find, if that makes sense. It's weird to say. The question we get all the time is, should I use a hammer or a shaker? Chad, what's the answer?
Either or both. Just depends on the structure and exactly what you're trying to accomplish. So for hammers, they're quick and versatile, and they may be the easiest way to go and set up. But there might be some instances where a hammer, you just can't excite the structure fully. So a shaker is going to be better suited for that. The flip side, there's going to be some structures that are either just too large or some that are even too small and lightly damped, such that a shaker won't be able to or won't be the best choice to excite the structure in that case. But both can be used concurrently. A hammer can still be used to help you quickly get a feel for what the structure is doing, if it's linear, where to place the shakers, if you're going to use shakers. So they're both tools in your modal toolbox, wouldn't the other out. And sometimes you don't know which is best until you begin your testing.
And it's not even too goofy to say that some people, depending on your structure, may use a combination of shakers and hammers even at the same time. There's a lot of papers that are done both. It's probably a fringe case, but depending on your structure, it can be another situation. Some of the hammer pros and cons, like Chad said, you don't need much to make a hammer test work. We like to say that there's a little art to using a hammer, but I think the same can be said about using a shaker. You can get force really quickly. You can change not only the location, but the orientation of your hit. You could excite the structure laterally as well as vertically really quickly. Often with hammer, averaging is totally key. You can't even get on anything, a coherence measurement, for example, without doing multiple averages of any of these tests. And with the hammer, you often have an integrated force sensor built in. But, like I say, it is a personal method, so it can vary person to person. Even if you switch up doing a hammer test with the same team and someone else on the group does it, they may not have the same touch you do. There's things like choice of hammer tips that can affect your outcome or how you're measuring. We'll talk about in a bit. There's things like double hits, which are, you can tell really well in the time trace. They can be good or bad. There's great papers and they can't be good, but there's great papers that discuss, if a double hit is the worst thing in the world or not. But just check your data and start rejecting on your averages if you think it's going to affect it. You can start to fill out a modal matrix, if you're envisioning the structure as a mesh of data that you need to collect with force inputs and measured outputs. You can start to complete a modal matrix pretty well with a hammer, but it's a lot of timekeeping and record keeping, and your software should be able to keep up with it. And your space might be tight to actually swing something. All the hammers were shown here, except for that little hammer left on the top. they're all mostly held with a handheld, but we make things like what we call Frankenhammer here to get a lot of oomph out of a small swing space. There's something called a modal punch that you can actually excite a structure if it's really tight to see, like in a confined area. Yeah, kind of Chad showing the modal punch there. And then an automatic hammer that could be, one of a few ways. You could have, I think we talk about it later, but special hammers to excite like civil structures like bridges or something. Anything that you can kind of get adequate input into your structure and preferably measure the force that you're putting into the structure point is great. Some of the keys for hammer selection really just depends on the size of your structure. A point that we made, if you were on the session a few weeks ago, there's the bottom 3 hammers on the right table, all output 5,000 pound force. But really it depends. The mass is the important part. You're swinging a large number of mass, so that drop in momentum is really what imparts the energy. So you're putting so much more energy with a 12-pound effective mass onto a large structure than you would, something with 1 pound effective mass. So even though the hammer may be held with 2 hands, and you can kind of see this is a goofy custom hammer for a very large structure, but that force is really controlled by the hammer mass. And then when you're picking tips, we'll talk about that in a bit too, but that's really kind of customizing your frequency input that you're putting into the structure. But even the top, we make a little hammer that's adorable just to test things like disk drives and small things like that. So there can be different tips, and they have different compliance or different, if you can envision on a micro level, the way they're resolving that momentum change from a fully moving hammer to a stopped at rest transmission of energy. And you can envision, if you have a solid tip, that transmission is very sharp. It's very quick, the impulse. And so conversely, in the frequency domain, you're imparting a lot of frequency across a wide range of a lot of energy across a wide range of frequencies. So what that means is you're exciting the modes at the high frequencies. That may not always be the case. You may not always need that. Generally, the softer the tip, the lower the frequency concentration of your force impact is. An important thing to note is you may be interested in the, check your tips. Make sure that they're not hardened, as some rubberized or elastic type tips can get over time, because the sensitivity of the hammer may have changed. Some hammer calibration houses will offer specific individualized calibration and sensitivity of each hammer tip. That may be something of interest to you as well. And customizing what your input spectrum should be.
Yeah, so with the different hammer tips, you can ultimately, like I was just saying there, the softer the hammer tip, you really customize exactly what that high frequency is you're essentially attempting to reach with it. That is ultimately control both the mass and the hammer tip when it's all said and done. So you can kind of think of it, I guess, it's like a car crash in a sense. With that softer hammer tip and more mass, you're sort of squishing that tip more, so you're lengthening out the time of the impact, so that energy is really focused at that lower frequency versus extending up to a higher frequency of a hard hammer tip. So and then there's of course making sure that you have enough energy that you are generating into the structure. So typical rule of thumb there is just at least 10 dB to make sure that you essentially have all your modes of interest that are excited. And then no more than 20 dB over that entire frequency range of interest, just again to ensure that you have enough energy in those modes that you observe and measure and understand. So getting to shakers a little bit now. So shakers are your kind of the alternative to hammers. So quickly go through a few of the pros and cons of shakers. So shakers have the ability where you can really control your frequency content you're inputting into the structure, and as well as your force control. So it makes them a very repeatable method of exciting the structure. And your test times with that can also be a lot shorter as well, since you're not having to rove that hammer to repeatedly hit potentially dozens of points on a structure, depending on the type of structure. And with that, you can get a more complete excitation of the structure in one shot, even whether it's use of one shaker or multiple shakers with this type of excitation. So it's not to say you couldn't rove the shaker also if you have only one shaker at your disposal. That's certainly an option. So if it's a larger structure and you need to shift that around to excite a different area of the structure that you couldn't really get energy to at your first input point, that's something you do. A little more work though. So that's kind of leading into the shaker cons, is that it is a longer setup time, more care into aligning the stinger as you're connecting the structure to the shaker. And you do have some force limitations with the shaker that you don't necessarily have as significantly with the hammer. Like Bruce had mentioned, the larger hammers, they're able to measure up to 5,000 pounds force. Shakers are typically going to be a much lower force combination of size. In order to get a high force shaker, you would need a very, very large shaker. But then also the stinger's limitation there. You can only get so much force through that stinger before the stinger will begin to buckle or slip or something of that manner. And then the stinger could challenge in that it will vary the boundary condition of your part. So a very lightly damped part, having a stinger connected to it, can create some or add some stiffness to that part as you're measuring. Then, of course, space is a consideration with shakers as well. There's going to be some tight spots that it's just not going to be feasible to get a shaker, even with a stinger, maybe even a long stinger, connected to the part well, so that you can make a measurement.
And I'd say one other con too that we don't consider often because, as part of PCB, we think accelerometers grow on trees, but probably since you're not roving the input location much and you're still trying to essentially populate a giant matrix or mesh of data inputs and outputs, usually use a lot more accelerometers on a shaker test, which is fine. It makes it, you definitely minimize the observability variability, if that makes sense. Let's say you had a temperature varying object or environment. Having a bunch of shakers and testing, or having a bunch of accelerometers and testing with as many shakers are required to excite your structure fully, lets you get all your data quick. So all of your time concerns can usually go out the window with a shaker. But, if funds are tight, accelerometers usually are used in greater supply, larger quantities for a shaker test. The shaker selection is pretty similar to a hammer. You're going to have frequency considerations, size considerations, and, force considerations, I guess.
Yeah. If you're testing a smaller part, there's really not any reason you're going to need a larger shaker with a higher force output. Not to say you can't use that larger shaker if that's at your disposal, but if you're starting from scratch and you're testing small, circuit level components or something of that sort, there's not a significant reason to go towards one of the larger modal shakers. That's a little better suited for something like a GVT test. And there are some differences between larger and smaller shakers too. So our small little smart shaker is seen right here. Great for still relatively small parts, you can see on that table that we have there. And it also, with its size, makes it easy and quick to set up, and very easy to use multiple shakers with that as well, with the amplifier built in. Now, as you move up, though, say you're doing something more like, we're going to kind of jump to the other end. Let's say we're doing NVH or a GVT test. This is where the 2060E is really kind of, I guess, one of our favorite shakers. For the force output it has, and it's got an extended stroke, which is very valuable in some GVT testing, where if it's mounted midway on a wing, which can have some rather significant motion, can be very valuable in that sort of testing. And it's still relatively small shaker and easy to use.
And again, the stroke, just by the laws of physics, you need a little bit more displacement on your shakers. You can really excite lower frequencies with more energy. So when we talk stroke about a shaker, that's what we're just.
Right. And then, to kind of come back to the middle where we sort of have a number of shakers we can use in your body and weight and similar type testing. This is where shakers that are sort of mid-size, like the 25E, can be great. They still offer the through-hole armature, which we'll show here in a second, discuss what its advantages are. But likewise, still have a little additional force over the smart shaker for those slightly larger items needed, while being small enough to just quickly set up relative to a larger shaker.
You can kind of see in the video here what a through-hole armature gets us. You can vary the stinger length. It allows for an easy connection to the part under test. You can kind of see the video for the demo. We'll send a link in again with the follow-up so you can see the video a little better. But the threaded rod type stingers need to be cut for length. If it's too short, just get a new one.
No, so the through-hole armature stinger or type shakers, they do have a specific stinger to use. As you can see there, it's this basically a straight rod versus a full threaded rod. So there are a few details on the stinger that you are using, but otherwise, yeah, as Bruce said, easy chuck and call it type setup. So there's no special tools needed for that. And it just makes it very quick to set up compared to a threaded rod that you kind of have to measure twice, cut once, sort of.
And you're fixed on, positioning them isn't a trivial situation. This, the through hole kind of eliminates one of the axes. And if you're trying to position two moving big heavy systems that you have to tightly position all three or all six DOF in space, it can be really challenging. So minimizing any of those challenges is great, and that's what the through armature allows you. Top shaker stingers.
Yeah, so stingers themselves. So what are they? They're just a simple rod essentially that we call a stinger. You might also hear it a quill or a push-pull rod or any number of other names. Probably most common is the stinger, and its main purpose is just to take the force that the shaker generates and transmit it axially along the stinger into your test part. So the idea is that it is laterally weak, though. So we don't want to impart any side loads into the force transducer. And we'll cover a bit more on the force transducer here in a second. The quick answer is that the force transducer is not built to measure those side loads.
And we have a white paper that we'll include with this as well.
Mm-hmm. Yeah, we have that. And then so we'll link that. And then, a few quick things to remember with the stinger, though, as we kind of were talking about with through hole, is that alignment is critical. So avoiding any bends in that stinger that might create a side load. Stinger length is something that will certainly affect your part and your measurement. A longer stinger can kind of have some buckling to it, whereas a shorter stinger can actually add some stiffness to your part. Same thing with the stinger you're using. A thicker threaded rod stinger can more easily add some stiffness to your part where it's connected, versus that thinner stinger shown in the picture there that has a little more lateral forgiveness, so to speak. And even where you're mounting the stinger on your part can be a very critical consideration. We certainly want to try not to mount at the node of one of the nodes, but at the same time, if you have a mode that has significant motion, that can cause a stinger to bend as it's moving with the shaker, and that can have create some measurement variations. So certainly a few things to think about as you're connecting that stinger, how and where to your structure.
What type of stinger, what kind of length you're using. There's considerations.
And this is just a view of the various stinger types. So common stingers that we have here at the Modal Shop. So the threaded nylon stinger that has a support sleeve on it, we commonly use with their smaller smart shakers. Those are at least a bit easier to cut down than your threaded stainless steel rod. And then your typical stingers that are thinner in diameter, so they're just the smooth threaded rod, as was shown in that last picture. And then one that maybe isn't talked about as much, but still can be very handy, is the piano wire stinger. So it, of course, has very weak laterally. So the way you use this is you're actually going to pull a preload on the part by pulling the piano wire through the shaker. So this particular type of stinger does require a through armature shaker. So you can pull that wire through it and then use the collet attachment to clamp to the wire and kind of pull a small preload on it. And then the shaker just essentially actuates over that preload. I think kind of a honorable mention, so to speak, it's called an inertial shaker. So it's a little different than the shakers we've sort of been talking about relative to the stingers so far, in that it mounts directly to the structure. So no stinger involved necessarily. You can mount it directly to the structure as the shaker, or you can actually mount a force transducer in between the shaker and the structure. So this is kind of great for tight spaces, or great for stuff like transfer path analysis or other transmissibility studies.
Thinner panels.
Yeah.
Lightweight structures that are hard to reach. It's perfect for.
Mm-hmm. So it's a little different animal than your typical modal shaker, but a very handy extra tool as another method of excitation.
Some of the options for dynamic force transducer, you'd want to match it to measure your shaker output force. A nice thing that you can do is what's called an impedance head. It's really a force sensor and accelerometer that are collinear, so you can really get your driving point measurement, which isn't important. Otherwise, you're messing around with putting an accelerometer right next to where your force sensor is, but they're not at the same point. So an impedance head is key. And the impedance head is normally offered in almost one size fits all kind of applications. And like we mentioned before, if you use the impedance or dynamic force transducer, put them at your object under test. It's a sad coincidence that the 1032 is a common size for a lot of things. So people sometimes just want to put it on the shaker, and it's wrong. So don't do it.
So just like the stinger, how mounting, we were talking in broad terms before as far as how you mount your stinger plus force transducer to the structure. The force transducer itself, or impedance head, does have a specific orientation you need to use. So the impedance head actually has etched on it, for example, mount this end of the test structure. Your typical force transducers, like the 208 series, they will just say top and base, but you'll want to mount the top side of that to the structure. Ultimately, this is because of the way the structure is designed itself, or sorry, the way the transducer is designed itself. It has a certain mass and stiffness, and the manner that they're calibrated, they are meant to be installed in a certain way so that you can essentially make the correct measurement. Installation itself can be, if you have the ability to stud mount it, that's always a surefire way to have a good mounting surface to your structure. But probably more commonly is an adhesive mount. So using some sort of super glue or two-part epoxy with the adhesive mounting base in the vast majority of cases is more than adequate for installing the sensor onto your structure.
Like I mentioned before, you don't want to measure the stinger's effect. You just want to know what the force of the shaker is actually being applied to the object under test. So we'll just keep hammering this point home. You can kind of see here what kind of effects you can see in your data if you're mounting the force transducer on the shaker side of the stinger instead of the test article. It's just something that's done a lot, and once your setup is set up, a lot of things look about the same. So you just look and see your data looks funny. So if you have anyone new in the lab, or you didn't have your coffee that morning, just double check where you've positioned things.
Then, why do we mention this, or why do we care about that dry point measurement? So dry point measurement is it's another great tool that you can use when setting up your modal test to help alert you to if you have a good position for your hammer or shaker even. So a driving point is going to show you all the modes of a structure that excited from that particular input location. So it's easy to essentially use a modal hammer and kind of co-locate a accelerometer close, or if you have a panel on the other side where you can impact with a hammer and make some quick driving point measurements. But then also when you get more into the math side of it, that this is used to properly scale your mode shapes and calculate stiffness. So another reason for paying attention to having essentially correct mounting and good mounting of your force sensor and stinger combined. So shaker quantity. So how many shakers should you use in a modal test? There's really no hard and fast answer to this one. The quick answer is enough so that you can fully excite and observe the structure you're testing. And of course, avoiding mounting your shaker at node locations of modes that you're interested in. So whatever that may take. And again, you can certainly rove the shaker as well if you don't have those shakers. So multiple is of course nice, anywhere from 2 to 4. Even smaller structures that might have very closely repeated roots can be very valuable to have 2 or 3 shakers. Again, there is a paper on this that we will link out in the follow-up email as a comparison between 1 shaker at high force and multiple shakers at low force. But you can see how we were able to pull apart these closely spaced modes, even on a smaller item that we can't with just a single shaker. Kind of a typical rule of thumb we found is for like body in white and automobile structures, 2 to 4 is good. Get to larger items like a ground vibration test for aircraft, kind of in that 3 to 8, depending on the aircraft size. It's good.
Yeah. So really just hammering what we said, more force isn't better. Historically, people would do something where they just put a shaker on part of the structure and turn it way up. That isn't really the best method to observe all the modes. And the paper kind of goes into more detail about that. One way that you can provide lateral excitation, positioning a shaker isn't trivial. It's a quirky little odd system. Here we have a weird lateral excitation stand. Our model 2050A lets you take any modal hammer and mount it horizontally. You can use it with the piano wire. It lets you easily control the stinger length. It decouples the motion of the shaker from the stand. And you can also use inertial masses. It'll add impedance to the shaker. Otherwise, the shaker would swing easily when it's connected to the test structure. So think about it. I've seen shakers mounted in all crazy ways. So it's kind of handy to have a tool to let you easily adapt where you're going to apply the shaker and the force. Test article support, there's a lot of methods. You can use foam. Oh, you want to talk about this foam?
Sure. Yeah. It's one of those things where it does depend on exactly how you are aiming to test. Most often we think about it, we're trying to mimic a free sort of boundary condition. So that's where things like bungee cord, shock cords, or the air ride that we have here, the 8032S, that is great for larger items like body and weight testing, or even other just hefty items that you really can't realistically put on a piece of foam or with some bungee cords of that sort. So they're great ways to quickly approximate that free sort of boundary condition. But you might also be testing in a loaded condition, as it were. So you might be testing some item that's always going to be used with a certain payload on it, and in reality, so you want to actually have that load on it that it experiences and test it with that. So it might not be a free boundary condition, but more of an in situ kind of test. So a number of ways you can support it. We've got a few tools that can certainly make life easier for that free approximation. But also just that is a detail to keep in mind during your test setup is what is appropriate for what you're trying to learn during your test.
There's a good paper that we'll also link. Again, keep adding more to your homework pile, but it's summer homework, I don't know. The response accelerometer sensors, there's some good app notes that our sister company PCB provides. But things to consider. I mean, if you're generally doing a typical modal, consider a constant current like an ICP type sensor. It's great for general purpose. You can have options like TEDS, which is the internal data sheet, easy to set up. Simple 2-wire systems. Low frequency setups, you may consider both DC capable sensors and the data acquisition. Don't automatically AC couple your input. For high temps, you can use charge mode piezoelectric. You can go up to 500F on some or higher. Yeah, or 900. Yeah, 900F, some higher. And pay attention if you need single or triaxial, or some points need to be a mix, or your test needs to be mixed. Remember that mass loading, and again, I think smart people do dumb things all the time, but if you just fix on a certain sensor for your entire structure under test, you may be putting heavy sensors on a lightly damped thin panel, for example, and just kind of forget. It doesn't seem that small and dainty when you're putting the sensor on. That mass of that object's changed the performance of that object. So just be cognizant of it. And like Chad alluded to earlier in the presentation, consider using dummy masses. Test your object on certain key parts with or without that mass, and see if, or put 2 masses on or 2 accelerometers on, see if your data looks different than one. You can start to get the idea of the effects of mass loading. And then phase match is an important thing for response transducers, the accelerometers. Like a PCB, for example, we have a 333 series where they're closely phase matched, just within a few degrees. If you're doing modal, phase is an important characteristic that isn't often important for other people doing general vibration testing. So keep that phase consideration in mind when you're selecting transducers.
Yeah, and then we've touched on this a few times already, as far as be mindful of where you're locating your sensors. As far as are they at the node of a mode, or if you're trying to validate an FEA model, you may have locations chosen already based on an FEA model. So how you're mounting your sensors can be rather critical to make sure you're getting usable data, so that way you can take your next steps in your design phase. And then also mounting, just how are you mounting? What's your frequency range of interest? Typically, modal testing is relatively low frequency in what we're hunting for. So in many cases, petro wax may be adequate. From there,
hot glue even.
Yeah, or even hot glue for say large items, like if you're testing on a wind turbine blade, which are
the modes will all be below 150 hertz maybe.
Right, and using larger sensors for that matter too. So from there you can use a tape, a low magnet, and then when you get into your adhesives like a super glue or cyanoacrylate or a 2-part epoxy, that's going to be great for high frequency response. I guess really, when in doubt, if you can just use a super glue with the adhesive mounting base that's included with many sensors, if the sensor isn't just meant to be adhesive mount to begin with, you will be in good shape as far as frequency response there. Stud mount is also, of course, great, though maybe not terribly easy to drill and tap holes in your particular test structure. So,
and this is one of those things that poor engineer has a decision tree decision to make as well. If you're testing for someone and the object under test is super precious, maybe using the Kapton tape or something that's non-marring or non-marking or doesn't leave any residue behind is great. Just consider all the effects that it may have on your test downstream. Some other options, accels aren't the only responses methods of taking data. You could use like a reusable dynamic strain gauge, like we have this model 740B02, or a traditional foil strain gauge. It may be longer setup. You could set up one of these dynamic strain gauge top. It even powers up with an ICP traditional channel. You could set it up in a minute and then take it off when you're done and be off to the races. There's actually a great paper, I promise the links that we'll send will be fantastic if you want to deep dive on any of these topics. But it was co-authored by Siemens, the Aeronautical Institute of Technology in Sao Paulo, KU Leuven, and PCB. It's great that shows dynamic strain sensors in conjunction with accels for GVT testing of an aircraft. It provides both strain and displacement mode shapes. It's a really interesting paper to closely see closely coupled modes on an aircraft. You could use non-contact things like a laser vibrometer. It can be expensive, but if you really can't put a sensor on it due to temperature or location, but you have a line of sight, the laser's great. You can even do a scanning laser at more cost, but and again, assuming your structure is time invariable or your system that you're measuring. And you can join microphones with the test as well pretty easily. I don't know how you want to.
Yeah, I mean, it's I've experienced a few things where some mics are placed very closely to the surface of the panel that was otherwise affected by a sensor being mounted on it. Something as nice as a laser vibrometer wasn't quite available in that case. So, there'll be the challenges there using something of that sort, but it's still another option or idea to kind of sneak up on what you're trying to learn from the structure, given what you have available to you.
Holy wow. We only have 100 more slides. Just kidding. But Chad and I discussed how everyone doing a modal, something like this, it takes forever. And we do have just a few more slides here, but we've already gone over quite a bit on time. I apologize. But something about cabling. There's a lot of cable options. Consider the bend radius. Make sure that you're not measuring cable width as part of what you're testing. Usually modal shouldn't see so much displacement, but consider using things like extension cables, both for your single axis or triax. If you had something wet, you can use, we have IP68 rated cables for operation if it's dusty or humid. But tape your structure so it doesn't rattle and you're measuring something, not desired. Look for any cuts and abrasions on the cable. Often cables are put away at the last minute, and only there are not enough attention's paid to the poor cable often. Anything else you wanted to say?
No, I mean they're kind of your last thought, but your first problem when you don't get a signal that seems correct. So.
And again, there is a cable tips link there that we'll also include.
And kind of the last big troubleshooting tip here is using a tool just to give you a known signal into your channel so you can check it. So you don't know if it is a sensor that's being an issue, a cable that's an issue, what it might be. So we've got some little handheld shaker there that's just either 1G RMS or peak that's selectable. So it's a super easy tool to use to just verify that your channel is the channel you think it is. Because what if you mixed a cable up and you have a sensor and cable switched? Suddenly your data is not going to make a lot of sense. Or B, if the channel isn't working, you can help use that to troubleshoot. Okay, let's switch cables, check the cable out, check the sensor channel or that axis and the triax, and sort through what it might be. And for a more in-depth look, you can use something like the 9110D calibrator. So you can vary the amplitude and frequency level with that. So, let's say the sensor is exhibiting some weird behavior, but it seems to only be at certain frequencies. You can help sort out, there is a sensor failure potentially, but it's only showing itself at a higher frequency, depending on how that sensor failed. So a couple great tools just to use to keep your sanity when setting up a large test.
And then just keeping my sanity, I want to say, hey, quick plug for rental. If you need to perform a test with no budget, consider the Modal Shop rental. It lets you try before you buy. We have everything that we talked about in this. We offer thousands of channels of accels, dynamic strain, cables even that we test, hammers, shakers, digital, the full DAC system. We have a new rental price list out. And the nice thing is it's everything's calibrated and it's perfect for a one-time test or something that was unexpected and you don't have money allocated in that year's budget. And how do I remember everything we're talking about? Holy smokes. We're going to send a kind of detailed link this week with a lot of links about things we've talked about. There's resources available both on Modal Shop and PCB, either our YouTube channels or learn more sections of our website. And there's third-party people that offer different courses. There's a roving course offered by a lot of folks, and I think that with depending on the situation in a few months, hopefully we can get back to things like great courses offered by NavCon, things like that, modal short courses. University of Cincinnati, for example, offers a great summer course typically that can start getting into the whys of the math behind things. Why would you pick a certain window for a certain test? Things that are kind of out of the scope of what we were doing today here, but there's a lot of options that maybe we could consider. And if you had any other iterations for that, let us know and we'll include it in the links too. And fundamentals of modal testing, there's a classic HP Agilent paper that we host on the Modal Shop site. Great, 40-page primer on why you do what you do for the structural tests. And Avoidable from UMass Lowell has a great section of modal analysis, modal space articles is what he calls them. Just bite-sized, 1-page, 2-page questions and answers with a lot of topics. And if you ever have a chance to see Pete speak, either virtually or in person, I wholeheartedly recommend it. And wrapping up our half-hour thing here in about an hour, I want to say thanks.